Hi everyone, I'm Laura and I'm presenting this joint work with Mihir Bellare. We're both from UC San Diego. And this is about an enhanced way to encrypt with passwords, which we call flexible password-based encryption. And we use it for end-to-end secure cloud storage and for provably resisting partitioning Oracle attacks. So to get started, recall that encryption is symmetric when the key is the same for both parties. Password-based encryption is just a case of this when the key is a password. And the usual perception of this picture is that the encryptor Alice and the decryptor Bob are different entities, and this represents applications like secure messaging. The main target of our work, however, concerns the case where Alice and Bob are the same entity, meaning it's Alice who is both encrypting and decrypting using her password. One example of this could be doing something like using an encrypted hard drive. And the motivating example for us is cloud storage. So this is the case where Alice is encrypting files under her password. She sends them to a server for storage, fetches ciphertexts, and decrypts them locally. And this type of application turns out to be big in practice, and it actually turns out to require some new considerations from password-based encryption, which will be the topic of this coming talk. But before I go into those details, we need to introduce traditional PBE, which is the current standard for password-based encryption. This is described by the standard PKCS number 5, which was originally published in the year 2000. So encrypting message M under password P first chooses a random salt, so meaning encryption is randomized, then derives a key K by hashing the password in salt, and then K and M are input to a base symmetric encryption scheme, and then a ciphertext and a salt are returned. And the choices of base scheme that we have are things like AES GCM and other standard modes of operation. And the security of this scheme was proven by Bellare, Ristenpart, and Tesaro in 2012. And they proved that this scheme gives you NCPA-style privacy as long as the base scheme provides privacy. Passwords are hard to guess, and H is a random oracle. So in practice, H would instead be a hash function or a password-based key derivation function. So given that this traditional PBE scheme already exists and it has a security proof, why revisit it? And we give 3 reasons for doing so. The first is that PBE is being used for new applications, and in particular, it needs to meet some of the new security goals of end-to-end encrypted cloud storage. And second, there are new and surprising attacks on traditional PBE. This is a class of attacks called partitioning Oracle attacks. These were introduced in a 2021 Usenix paper by Len, Grubbs, and Ristenpart. And they implemented one against an application called ShadowSocks that was using PBE for secure messaging. And all of these attacks are active attacks, so they're making online queries, and so they aren't captured by any of the NCPA privacy definitions. And third and finally, symmetric encryption has itself moved on from randomized privacy-only schemes to AEAD, as represented by new standards like GCM. And so we would like to align PBE with modern symmetric encryption, which specifically means moving from randomized to non-space schemes, as well as requiring authenticated encryption rather than only privacy. So the main contribution of our work is what we call flexible PBE, or FPBE, for which we provide definitions, a proposed scheme, and proofs of security. So with regard to the first section, so definitions and syntax, we allow nonces and associated data and make the salt an input. So the point of this is making encryption deterministic. The other thing that's different from traditional PBE is that the salt can be reused as long as only the nonce changes, and this ends up being useful for some applications. And we give 3 security definitions. So the first one is privacy, which we call PIND, authenticity, which we call PAuth, and a simultaneous authenticated encryption goal, which we call PAE. And the scheme that we propose is called DTE, for derive then encrypt. This is a natural extension of PKCS number 5 to our setting. And you can note from the syntax that we build it from a base symmetric encryption scheme and a password-based key derivation function. And so the last thing that we do is we prove the security of this scheme. So if we assume that F is a random oracle and passwords are hard to guess, then if the symmetric encryption scheme satisfies the standard notions, then the derived password-based encryption scheme satisfies the notions we've defined for FPBE. So in particular, if the base scheme satisfies privacy, then DTE satisfies privacy. If the base scheme satisfies authenticity, then the derived scheme satisfies authenticity. And this last line, which is sort of the important one, is that if we additionally assume this property that we call KROB, which stands for key robustness, which I'll discuss later, then we actually get better security bounds for authenticated encryption. And these actually prove that the partitioning oracle attacks will no longer work. And so this last line, proving this is one of the main challenges of our work, and is sort of most of the paper. So before I go into those results, I wanted to have some remarks and limitations. So first of all, these results are assuming that on some level that passwords are well chosen and hard to guess. And so this is a necessary assumption for password-based encryption. There's no way to provide security when passwords are guessable, but our goal is to make our assumptions as weak as possible. And the second remark is that we assume the password-based key derivation function F is a random oracle. We have some intermediate results in the standard model, but in the end, we are using the random oracle model. And the general takeaway is that our scheme DTE provides authenticated encryption even without this key robustness, but we do prove concretely better security bounds when you do have key robustness, and these provably prevent partitioning oracle attacks, which is largely the question we had set out to answer and some form of the statement we had wanted to prove. So diving in, we can start with some definitions. So the syntax of an FPBE scheme involves encryption and decryption algorithms, as shown in the diagram on the left. Encryption is deterministic, taking the passworded message, which is the same as traditional PBE, but it's now taking the salt, nonce, and associated data as input. Decryption is deterministic as always. It's again taking the salt, nonce, and associated data. And the salt is reusable as long as the nonce changes, and in usage, the salt is chosen uniformly at random. As with the usual AEAD notions, we provide authenticity but not privacy of the associated data. And finally, there's no key generation algorithm. Instead, the key P, which is the password, can be any string of any length. So I don't want to spend too much time on these slides, but our first security definition is for privacy. This is also called confidentiality in a lot of papers. We use a game-based definition where we call the game pend, and it's parameterized by the scheme FPBE and a password distribution PD. And so the game shown on the left is simplified from the actual game in a couple of ways. So it's only showing one user. In the paper, we are considering multiple users, however many users are using password-based encryption. And there are a couple other simplifications for this slide. But essentially, the adversary is allowed to query for salts in this salt oracle. They're allowed to query for encryptions in this encryption oracle. And they're either going to get a real encryption or a random encryption. And guessing which case it is sort of how they win this game. And this is pretty standard to the normal end game, and so we call it pend for using passwords and adding the salts. And in general, privacy is just asking that ciphertexts look like random strings. And the second security definition is authenticity. This is also called ciphertext integrity in a lot of papers, and we call the defining game pauth. And the difference from the previous slide is we've added this verify oracle, and so now the game is saying that the adversary will win this game if they can create a valid tuple of salt, nonce, ciphertext, and associated data that decrypts to something valid. So this symbol is bot, so decrypts to something that is not bot. And authenticity is asking that it should be hard for an adversary to create one of these tuples. And in brief, we're asking that it's hard for an adversary to create such a tuple. So this is our third and final security definition for the talk. This is PAE for authenticated encryption. And this captures authenticity and privacy in an integrated way, and accordingly is similar to both of the games on the previous slides, but I won't go into the details. And the connection to privacy and authenticity is a theorem we proved, which says if a scheme satisfies both of pend and poff, then it satisfies this authenticated encryption goal. And the point of this theorem is to simplify proofs. So in the end, we always want authenticated encryption for schemes, but it turns out that it's a lot easier to analyze privacy and authenticity separately. And we actually proved this theorem with an additional simplification of only requiring authenticity to hold for a limited class of adversaries that are called sequential. So these are adversaries that make their verify queries all at the end non-adaptively. And so it's a big simplification, but the theorem still holds, and this makes a lot of our proofs easier. So I'll go into a little bit more detail on the two motivations in the title of this work, which were new applications and new attacks. The first motivation is the application of end-to-end encrypted cloud storage. So as you all probably know, end-to-end encryption means that the symmetric key is known only to the user and not to the server. And why are people using passwords for this is the question relevant to this talk. And it turns out that passwords are a lot easier to support access from many user devices. So if you want to access a server from your phone, your tablet, your laptop, you need to transport either a password or a symmetric key. And it turns out it's a lot easier to use passwords and not copying symmetric keys across devices. So the three examples on the bottom are some applications using passwords for password-based encryption today. The largest of these is Mega, and so they've recently claimed to be using 1,000 petabytes of password encrypted data, so it's important that we sort of get at least the theory behind this right. So cloud storage has many other needs, but these are just two of them. So these are two things we think cloud storage applications could benefit from. So the first of them is security. So recent attacks have shown that authenticity is especially important to have. So these attacks are on Mega, the application I mentioned on the slide before. And so if you recall that the traditional password-based encryption schemes are only requiring privacy, not authenticity. And so this is something that we add. And the second item is operational efficiency, which we don't do too much on, but I just want to point out that traditional PBE is especially bad at this. So the randomized encryption scheme is outputting a salt with each ciphertext, and salts need to be large enough to resist collision and foil precomputation, so they're usually 128 bits. So you have this 128-bit overhead for every ciphertext. In our definitions, using nonce cryptography, only the salt nonce pairs need to be unique, so we can require unique nonces instead of unique salts. And this saves us some ciphertext overhead, so the overhead is slightly less for flexible password-based encryption. And this was not a goal of our work, but is sort of another point that we need to be modernizing PBE for what applications are doing. And the second motivation to discuss is resisting partitioning oracle attacks. So this is a type of attack on traditional PBE that requires access to a decrypt or verify oracle. And in the 2021 paper, this was a ShadowSock server that was essentially providing a free ciphertext validation oracle. And the attack requires that the base scheme is not key robust, and most common symmetric encryption schemes, so GCM, ChaCha, none of these are key robust, and so they all would be vulnerable to this attack. And essentially it allows dictionary attacks with fewer online queries in various settings. And on the right, I've just recalled that the definition of key robustness. This is also called key committing, so they're essentially the same thing. But a scheme is key robust if a ciphertext is a commitment to the key. essentially asking that the ciphertext will only decrypt under one key. It's not possible to find a bunch of keys that the ciphertext will decrypt under. And so specifically, if an adversary is given some random keys, it should be hard for them to make a ciphertext that decrypts under both of them. There are a lot of variations of this definition. This is one of the ones we chose to use. And the question that we wanted to ask is that using a key-robust base scheme seems to prevent this attack in password-based encryption, and it's been recommended in practice, but it's not clear if you can prove that key robustness gives you a better security guarantee, or if key robustness actually provably prevents the attack, or if key robustness gives you any other nice security properties for encryption. And so this is the question that we ask, and it turns out that we can prove more with key robustness for the scheme we propose. So the scheme we give is called DTE, which stands for Derive Then Encrypt. It's pretty similar to PKCS number 5, but it's adapted to our new setting of non-spaced encryption and asking for authenticity. So very similarly, we apply the password-based key derivation function to a salt and password to derive a key K, which is used in the base symmetric encryption scheme. And choices of the base scheme again, there's AES-GCM, there's ChaCha. There are some newly proposed key-robust variants of these schemes. And choices of F include standard password-based key derivation functions, bcrypt, argon2, etc. We'll sometimes be modeling F as a random oracle. So now we move on to proving the security of this scheme. And I'll start just by giving the asymptotic results. So the first one is saying if the base scheme is insecure, so it provides privacy, then DTE is going to be pend, which is our password-based version of privacy. If the base scheme provides authenticity, then DTE provides authenticity. And if we additionally assume key robustness, then it still provides authenticity. So the second and third results are saying the exact same thing. So what was the point of assuming key robustness if it just made our lives harder? And it turns out to matter for concrete security. So it doesn't matter for asymptotic results, but it will matter for concrete security, to which I'll now turn. So before we talk about concrete security, I need to talk about guessing probability. And this is how we measure the strength of a password distribution. And we call it this GP of a distribution PD. The parameter Q is the number of guesses that an adversary is allowed. And we define the guessing probability as the chance that an adversary can guess a randomly chosen password in Q guesses. And a little bit technically, it's the maximum probability over all Q query adversaries. So this is not a computational term, it's a statistical term. But the key point is that in password-based encryption, we need to assume that this guessing probability is small, but the smaller the value of Q, the weaker the assumption is. So the smaller the value of Q, we're assuming less about the hardness of the passwords, which is generally passwords are not great, so we want Q to be as small as possible, and we do this in our proofs. So I'll just give a little picture of what our concrete results look like. So for privacy, this was our asymptotic result, and the theorem statement of this says something along the lines of, for any privacy adversary A, we can bound their advantage, so their probability of breaking the scheme, by some sort of equation with 3 terms, and we would like to make this sum of terms as small as possible. And the second and third terms, we already know how to deal with. You can choose a good base scheme, and you can choose a long enough salt length. And the term that is really, we don't know much about is this guessing probability with some parameter. In this case, Q is QH. But we can simplify this equation to just the term we're interested in. And the question that we ask is this Q equal QH the best bound that we can get? Meaning, is this the best parameter for which the theorem can be proven? And we show that this is true, and this is just shown actually using a brute force attack. So the privacy case has actually been pretty straightforward for concrete security, and authenticity is the complicated one. So I'll get into that one next. So we have a similar theorem setup, which I will mostly skip over, but we are giving the adversary some amount of queries to all of their oracles, and we're saying something about their advantage and bounding it by this sum of terms, where we have a guessing probability and a small delta, where delta is encompassing things that we already know about the scheme. And so we break it into two cases, if we're just assuming authenticity or if we're also assuming key robustness. And so this is simplified for the single user setting, but in the single user setting, these are the bounds that we get. So here we get QH again, and here we get QB instead of QH. And the point to make here is that this is giving us a tighter bound when QB is much smaller, which is generally the case in practice. So QB is usually something less than 3. You can do a lot of things like throttling verification attempts to make this small. The problem is QH is very large, so this is the number of offline hash computations, which can sort of be arbitrarily large. So at least in this setting, we're getting a much tighter bound when we assume key robustness. And in the paper, we analyze the full multi-user setting, and we get a tighter bound in more settings, but I'm just including this one in the slides. And the second question we can ask is, well, maybe this theorem 6.2 was just too loose, like we didn't prove it correctly, but it turns out that if you're only assuming authenticity, this is actually the best bound you can get. So this theorem is not actually loose, it's tight, and we're actually getting better results when we assume key robustness, which is what we had sort of wanted to answer. And the fact that this proposition is proved by the partitioning oracle attack sort of brings us back to our motivation of answering what partitioning oracle attacks mean for provable security. And I'll conclude just by a couple of quick remarks on the extended results. So it seems most of these results seem like they should be obvious, but it turns out to be hard to take advantage of key robustness in the proofs. And so we have a lot of tricks for doing this. Some of them we define some intermediate steps. So we have a notion of authenticity with corruptions. We have a new security definition for PBKDFs, and all of these help us with the final proofs. The final theorems are in a multi-user setting, and they cover different AE paradigms. And our results hold in all of them, and we have a pretty nice syntax for covering four different models that we considered. So I'll just end with a supply slide that we have at RSA. So I encourage you all to consider using key-robust encryption schemes if you're doing something with passwords, considering concrete resources in general. So in our case, this was hash and verify queries, and they actually turn out to matter in the theorem statements. And the last one is, this is only one application of key-robust symmetric encryption. This is a somewhat recent area in the design of symmetric encryption schemes, and it certainly needs more work and might have other applications. So thank you for listening. I'm happy to take any questions in the 1 minute I have.
So you mentioned any key length. Is there, like in practical implementations, better to have some sort of minimal boundaries for this?
I don't know. I haven't looked much at how this is implemented in applications. I think if you're asking about the ciphertext overhead part, I think the ciphertexts are usually like the much larger part. It's not necessarily the salt and nonce. But I'd have to look at applications to see.
Thank you. All right, thank you for coming. I'm Scott Yolich. I'm a faculty member at the University of St. Thomas in St. Paul, Minnesota. This is joint work with my faculty colleague, Sarah Myracle. So I'm going to talk about deterministic format transforming encryption and some new constructions that we have for that. So format transforming encryption was introduced about 10 years ago at CCS in 2013. And I'll have a little bit more detail on the next slide about like what it is and an example there so you can understand this. But essentially, it's a way to encrypt messages so that the ciphertext you get look a certain way. You want the ciphertext to be in a desired format, and you want to be able to basically take a message in one format and translate it into another format in the ciphertext. So the original application of this was censorship avoidance, so trying to get around like deep packet inspection. And the original schemes were actually included in a Tor browser bundle. And then there was a later paper about the next year by some of the same authors and some others where they introduced deterministic format transforming encryption. And that brought in some other applications like encrypted database compression. So we're going to be focusing on this latter notion, deterministic schemes, we're going to see. So to make this a little bit clearer, what is format transforming encryption? We see the syntax with the top diagram here. So coming as input here on the left, we have the traditional symmetric encryption inputs, a message and a key. What's a little different is you also now are specifying an input format and an output format. And you could specify these in different ways. I'll typically be talking about them as like regular expressions in this talk. So for example, we see down here, the input is going to be this 5-digit number. And the format here, actually, it's digits 0 through 6, and then 5 of those. Okay, so it's kind of like a base 7 number here. And then the output format, the desired ciphertext format, specified with this, kind of made up some regular expression here. So an A followed by 1 or more B's and C's, followed by an A, followed by 1 or more B's, and then with total length 20. And so you see in this example, you can encrypt this base 7 number here, 63352, and you get this kind of long string matching that regular expression for that ciphertext format. Okay, so ideally you'd be able to do this and kind of specify arbitrary formats for the plaintext space and for the ciphertext space. So the original schemes, the ones that got included in like that Tor browser bundle, were randomized schemes. And so our focus instead is on building new deterministic format transforming encryption schemes. And so this is particularly important if you think about how many possible messages there are and then how many possible ciphertexts there are based on the formats. This is going to be particularly important when the number of ciphertexts is only what I call modestly larger than the number of messages. So say there's like 20 times larger ciphertext space than plaintext space. In such a situation, there's sort of not room for a randomized scheme and the stretch you might want to get from that. So it seems like a deterministic scheme is what you would desire there. One thing you might have heard of that's a special case of this, if the input format matches the output format, we have the familiar format preserving encryption schemes. There's been a ton of work in that area, both in academia and in industry. So you might have heard of those. And foreshadowing a little bit here, some of the techniques that are really useful there in format preserving encryption are going to be useful for us to help build new format transforming encryption schemes as well. So let's give a little background on how can you construct such a thing, right? It sounds really cool, hopefully, this format transforming encryption, but how do you do this? And one of the challenges is that the plaintext format and the ciphertext format could be very different. And so it'd be useful if we had sort of a common language. And think about the example I gave there. They don't even share the same symbols, right? One was like digits. One was these letters, A, B's, and C's. So there's not even the same symbols involved in the plaintext and the ciphertext in that example. So it'd be nice if we had kind of a common language to work with. And so what we're going to do, what previous work has done, both in this and in format preserving encryption, is sort of use integers as our common language. So ranking is a key part of format preserving encryption, and it's also a key part here of format transforming encryption. So the idea of ranking is you're basically just taking all of the plaintext and the ciphertext you're interested in and mapping them to integers. Okay, so you got this plaintext over here, we're going to map it to this integer. We got another plaintext, we're going to map it to a different integer. So example here, I think my example ciphertext from the other slide, you'd have some rank algorithm that takes into account what this format is. And maybe it says, oh, yeah, for this particular input, that should be 35,007. That's like the number we're going to assign to that thing. So you want this to be efficient, this rank algorithm. Then you want to go the other direction as well. So given the integer, you want to go back to which ciphertext in this case, or plaintext, does this represent. So you send in as input 35,007, and it spits back out this long string of A, B's, and C's. So it's very useful if we can have these rank and unrank algorithms, because that's going to allow us to really just reason about integers, as we're going to see. So we're going to be talking about two different types of ranking here. And we give them the name strict ranking and then relaxed ranking, which is actually introduced in that second FTE paper that I mentioned from 2014. So with the strict ranking, we've got our possible plaintext over here. And when we rank, we're able to map them like perfectly into integers starting, let's say, at 0. And they're really packed in there perfectly. Notice there's sort of no gaps between them. You've just perfectly packed them in, so it goes up to 0, up to, let's say, the size of the set minus 1. Right? So every integer is just sort of perfectly mapped to this most compact range of integers. And then you can go back the other direction as well. You can't always necessarily come up with this. And so for certain formats, it might be easier to instead come up with this thing called a relaxed ranking. So here, again, you have the messages you're interested in. This could also be the ciphertext that you're applying this to. And now you're still mapping them to integers, as we see over here, but they're not all kind of packed together. Now they're maybe spread out. There's some gaps between them. So you're still mapping them to integers. You can still do the reverse direction, go from the integer back to the message in that format. But now there's kind of gaps in here. Not every single integer is being used here. Okay, so we're going to be talking about both of these. Sort of looking forward, the relaxed ranking case is sort of much harder to deal with. So that's where our main results are going to be. So once we have this ranking, that was kind of background, here's basically how you could build format transforming encryption. It's actually not too hard once you have the idea of ranking. So you start on the left here with your message, you rank it, and you're getting, here I have a relaxed ranking shown, which eventually is going to be where I focus my efforts here on this results. So your message is going to get mapped to one of these purple points over here. Think about this entire kind of white rectangle as this big set of integers here. So you're going to rank your message. It's going to end up, let's say, up here, one of these purple points. And then what we're going to want to do is apply some sort of encryption-like object here to randomly map that to one of these gold points or yellow points over here. So it's going to map it to some other integer. And then we can unrank that integer into the ciphertext space. Okay, so if you have the ability to rank and unrank both plaintext and ciphertext, you basically translate your message into some integer. You encrypt that to another integer, and then you translate that back to the ciphertext in the ciphertext format. So the big question mark here is, I have 3 question marks in the slide, is like, so what is this thing in the middle here? Because you got to make sure that you're actually mapping the purple points to the yellow points correctly here. And so the big challenge is going to be kind of coming up with the right thing to plug in to the middle of this pretty well-known construction that also works well in format-preserving encryption. So if you want to think of this as, what's the cryptographic object we're interested in, this object has actually been studied under a couple of different names. We've gone with a name that most recently was used for this by Boneh, Kim, and Wu at TCC 2017, which is an invertible pseudorandom function. But previously, Ragway and Shrimpton had studied essentially the same type of object, and they had called it a pseudorandom injection. There might be other names for such an object floating around as well. And essentially what we need to be able to do is build these for very specific target domains and codomains, kind of which subsets of integers we're interested in. We need to be able to build an object that works for those particular sets. So we have to target those domains and codomains, so we call these targeted IPFs. And you can see the paper for more formal definitions of this cryptographic object and some more minor results as well. For the rest of this talk, I'm going to focus on what I consider our main result. OK, so let's try to start understanding how to build this thing in the middle. So once we can rank and we can unrank, that kind of middle part of that diagram is the big question here. How do we map the purple point to the gold point? So it's a lot easier in this case. So this was the strict ranking picture, right, where when we rank, we can get the points all kind of compactly put together into the top range of the integers here. And so what we really want to do here is map some point in x. X is what I'm calling the purple area up here, to y, which is what I'm calling this gold area here. And we're going to say z is this kind of bigger area of integers as well. So maybe this is like a power of 2 to be convenient. And you're not necessarily using every single number here. You're just using some subset of those integers. So our main building block here is, well, let's say that we have a way to encrypt things in z, this bigger set of integers. So I'm going to say we have a permutation on z. Okay, so think we have a cipher on z. We want to try to use it to map a point in the purple region to a point in the gold region. So here with the strict ranking, it's going to turn out that a familiar technique from format-preserving encryption is going to work well here. So something called cycle walking. So if you've never seen cycle walking before, it's kind of a fun technique for doing format-preserving encryption, kind of manipulating permutations. So essentially what you do, kind of go back to the previous slide here, again, what we're trying to do is map a point in this purple region to a point in the gold region. So what you can do is you can apply a permutation on this bigger set Z. Now what can happen is you could end up mapping your point down into this bottom white region on the right side of the diagram here. So you sort of missed the gold part. So what do? You missed it. Do you give up? No, you just actually apply the permutation again to that point. So let's say you ended up down on the right here. Well, apply the permutation again there, and maybe finally that maps you into the correct region, that gold area. So basically you say, oh, apply the permutation to the point and check, is it in Y? If not, apply the permutation again. So it becomes this kind of nested permutation here with 2 applications of pi. Check if that's in Y. If not, try it again a 3rd time. So you just keep doing this. So this is called cycle walking. And the name comes basically from this diagram here. So every permutation can be broken down into disjoint cycles, right? That's a way to think about an arbitrary permutation is a bunch of different cycles. And essentially what's happening here is, again, what we're trying to do is map a purple point to a gold point. So I'm coloring the points here. Remember, the way we have it, purple is actually like a subset of gold here because they're all packed together at the start of the integer range. So we actually have points that are both in the purple and the gold, and then there are some extra points in the gold region, right? Those are the gold circles here. And then the points that weren't in either of those, remember there was still some area in the bottom of those white rectangles. Those I'm showing is just a white circle here. So what can happen, right, is you apply the permutation. Let's say this is your purple point. You want to map it to a gold point. So you apply the permutation. That basically goes 1 step in this cycle. Now you land on a white point there. That's not what you want. So what you do is you apply the permutation again. That corresponds to going 1 more step in that cycle forward. You're still not where you want to be because it's another white circle here. But if you apply it 1 more time, then you do hit a gold point there. Okay, so basically you can just keep walking around the cycle until you hit the point you're looking for, a gold point in this case. And so you can see from this example, and this will be true for any example when we have this strict ranking like this, that eventually you're gonna find a gold point. You could even have a situation like on the bottom right here, where it actually ends up going right back to itself. But because every purple point is also gold here, that's fine. Purple got mapped to gold still in that case. Okay? So this is how cycle walking works and could solve this problem when we have strict ranking for both the plain text space and the ciphertext space. So the harder situation where our results are focused is in this relaxed ranking setting, right, where you have the gaps between them. So you've mapped your plain text into the purple points, kind of spread out among these integers, and then you now want to map one of those purple points to one of these gold points over here, again, sort of spread out among the integers in probably a vastly different way. So we're trying to do this. Again, we have to build this box here in the middle. So a natural thing to do, and what previous work had suggested, is let's just try to do the same cycle walking idea again and just see what happens. So now let's look at this. Now we actually have 4 different types of points, because now you can have points that are just in x and not y. Right? So some of these points on the left over here, they could be purple, but if you kind of look across to the right part of the diagram, they might not be gold on that side over there. So now there's 4 different types of points here. You could get a point that's in x but not y. Again, like we had before, it's in both, so it's sort of shaded both purple and gold here. Points just in y, gold, and then the ones that are in neither, kind of in that white area of those boxes, shown as the white circle. So some of these, just applying cycle walking, you're going to be fine. But now, as it's highlighted there in the top right, you can get cases where the algorithm's going to fail. Right? Because your end goal is to map every purple point to a gold point. And you need to do it in a way that later you can decrypt, right? So you need to be able to reverse this process. But what happens here? Well, we actually have 2 purple points in this cycle and 1 gold point in this cycle. So, you can't have each purple point get its own gold point in that situation at all. And so it's sort of, what do you do in this case? Well, the algorithm is going to have to fail right here. Okay, so the previous work had suggested doing this, but they were very careful to say, yeah, you only really want to do this if you have way more gold points than purple points, right? So when your ciphertext space is like massively larger than your plaintext space, then this case should be very rare, and it shouldn't really happen very often that the algorithm fails. So this is kind of where we're focused on our work here, Because as I said, well, it seems like the most useful case, though, for deterministic format transforming encryption is when actually the ciphertext space isn't way bigger than the plaintext space. Maybe it's just 10 times larger or 20 times larger. You don't really have room for a randomized scheme and the stretch you need for that. And so it seems like a deterministic scheme is what you need in those cases. But those would be the exact cases where that failure would start to become a problem in your algorithm. So this is where we're focusing our efforts here. And our main result here, again, there's a number of more minor results in the paper as well, but what we consider our main result is we introduce an alternative to cycle walking here. We call it nested n-cycle walking. And if we use that in place of traditional cycle walking, which I just described, we end up basically solving this problem, getting rid of this failure probability, and it's going to give us new constructions of deterministic format transforming encryption. So let's go over this new technique, this new type of cycle walking, nested n-cycle walking. So now what I've done here is I've replaced the permutation with an n-cycle theta up here. So what is an n-cycle? Well, it's also a permutation, but it's a special permutation where there's only a single cycle. Every single point is in just one massive cycle here. Okay, so instead of a bunch of disjoint smaller cycles, there's just one massive cycle. So this is sometimes called an n-cycle, sometimes called a cyclic permutation. So we're using the term n-cycle for this. So intuitively, the reason this is going to work is that we're not going to be able to get that case that I had highlighted in pink or red on that previous slide where we had the 2 purple points and only 1 gold point. Now every point is sort of there eventually in the cycle. And there's more gold points than purple points. And so kind of every purple point should eventually find a gold buddy to pair up with because everything now is just in this one massive cycle. So intuitively, kind of conceptually, that's what's going on here. That's why this is going to work. So now we're able to start walking along the cycle. And again, we want to try to map a purple point to a gold point. So the problem, though, is you could run into a situation where you have a purple point here, let's say, and on the way to a gold point, you could run into another purple point. And so that's a situation we have to deal with, and that's where the word nested is going to come into the situation here. So with nested n-cycle walking, you sort of do the usual cycle walking thing. You start walking around the cycle. You apply, in this case, the n-cycle. Check if you get a gold point. If not, do it again. Check if you get a gold point. But now there's this big but right here. If you first encounter another purple point, another point in X, then the point you started off with sort of moves back in line 1 spot. It's no longer at the front of the line. It's no longer going to get the next gold point. It's going to have to wait. This new purple point that it encountered, that's now at the front of the line. That's the one that's going to get that next gold point that's encountered. So this is kind of where this nested name comes from, because if you kept encountering purple points, as we're going to see in a future slide here, you'd get this nested structure. I'll have a diagram to show this in a second. So just to illustrate with my particular picture from the previous slide how this would work, kind of the interesting case is the one I highlighted before at the bottom here. So we start with this point X, this purple point, and we're looking to pair it up with a gold point. But on the way, we encounter X prime, another purple point. So that means X prime now is sort of at the front of the line. It has the highest priority for getting gold points. And this original point we started with, X, now is kind of like second in line. So when we encounter a gold point finally here on the next step, the more recent purple point gets paired up with that one. Okay, so X prime ends up getting paired up with this gold point. But then luckily down the road, we encounter another point with gold on it. That's the one X is going to end up getting mapped to. So it just had to wait a little bit and kind of get the next one. Okay, and so these are the sort of the pairings that end up happening here based on these arrows that are being shown. So there, of course, is a bad case. Anytime the word nested is involved, you could worry about very deep nesting. And so let's say our n-cycle looked like this, right? It was a bunch of purple points followed by a bunch of gold points. Well, if you want to start encrypting this very first point over here, it keeps having to move back. Every time you hit a new purple point, it sort of moves back in line a spot. And so when you start hitting the gold points finally, the most recent purple points get mapped to those, and the original purple points got to wait a long time before finally it finds a gold point that's sort of all its own, and it doesn't have to wait any longer. So basically, we show in the paper that for the sizes of these sets that we're dealing with, where maybe y is 10 times the size of x, and as long as we're choosing a random n cycle, then this is very unlikely to occur, and you actually get a low expected time that you would have to walk through this cycle. And to get a random n cycle, basically you can apply this result of Narrow-Reingold. You can get a sort of random permutation with any cycle structure you want by applying a random permutation, then a fixed permutation with the cycle structure you want, and then the inverse of the original permutation, and that gives you a random permutation with the desired cycle structure. So if we plug in for theta in there, just sort of any n cycle, we end up getting a random n cycle out of this. Okay, so putting this all together, basically into the kind of the original diagram here, what you're going to do now with nested n cycle walking, you're going to rank your message. It's going to give you some integer. You're going to do nested n cycle walking with a random n cycle. That's going to get you what we were calling a gold point y here. Now, a slight thing, you don't kind of have enough randomness involved at this point because it was just an n cycle that was used. So you do have to kind of do one extra random permutation at the end to kind of do a little bit of extra mixing. So that's that extra box being shown right here. But then after you do that, you do get this point y prime. It's another integer that's going to be, as I was calling it, gold in those pictures. So at that point, you can unrank and get back a ciphertext with the desired format. Okay, so this is kind of the final construction here, where our big new contribution was this kind of green box here, the nested n cycle walking being plugged into this. And we go over a specific example in the paper so you can see that. Okay. So, take away from this, I encourage you to play around with format transforming encryption. The previous work I mentioned from 2014, they did publish like a Python library you can use called libfte. So I encourage you to play around with that. We're currently working on implementing ours as well, kind of making it play nice with libfte. But feel free to reach out if you have cool ideas for applications of format transforming encryption, or cases where you think specifically deterministic format transforming encryption would be a useful tool. So thank you.
Hey, Scott, I think on slide 13, you showed a situation where the standard cycle walking fails. And it's clear that correctness fails, but when you say that the algorithm can fail, does it know that does it recognize that it's failed and can give some error in that case?
Yeah, it can recognize that it fails. So, you could potentially do other things as well. I mean, you could apply a different cipher in that case or something like that. But again, it's sort of what do you do in this failure case? So, ours is an alternative that you can't get failure with ours. You could potentially get unlucky or something and have to walk around the n cycle a while, but it eventually will get a point. It just might take a little bit more time.